Warmest greeting for everyone. Today I'm just going to give a training on HEC-HMS model, which is a hydrologic model. Hydrologic model plays a significant role, especially for the investigation of the hydrological process, like flow characteristics. So so this model, this HEC-HMS model, is designed especially to simulate the precipitation runoff process of dendritic watershed systems or complex watershed systems. So it will help us, mostly helping the hydrologists, especially water resource engineers, hydrological science, to deal with the precipitation runoff scenario condition in hydrological system, and it is designed to be applicable in a wide range. So in terms of applicability, this model is applicable in a wide range of geographical areas, even if at continental level you can apply, world level you can apply based on the data availabilities. So it has no limits from the small watershed to the larger watershed, the model of capability of applications. So let us see the physical description of this model. How this model described it, this model have a model watershed sections, which is named as in this HMS. There is a basic model which gives a detailed description about our watersheds. So our basin, it divides the basin of the watershed into a sub-basin, sub-watershed, ridges, and junctions, reservoir, divisions, source, sinks. So here, sub-basin, just it showed the number of the sub-basin which is available under our basin. Now, for example, you can see here. Let's say this is the screenshot that I took during this model training. So here, by default, it will give you a basin models. Okay, this basin models, which have a physical representation of watershed of a catchment or sub-basin or watershed. So in this case, under these sub-basins will have the basins have a sub-basin sections, and ridges means river. Okay, this indicates the river, and junctions, the place where the river, two rivers are meeting, junctions. Reservoirs, which is available in our catchment, maybe reservoirs such as dam, or even if there is small lakes or oceans or seas or dams, and diversion structures. Okay, and sources from where the water is flowing to our rivers. Sinks, okay. Sinks are the outlet of our watershed outlet. So these are the physical representation of how the HEC-HMS represents the watershed or the river basin in the sub-basin or basin model sections. How it represents our catchment or our watershed. We are coming to the approaches or the methods which are helping us, because as we said, this model is very important, especially for dealing with precipitation or of analysis of dendritic catchments or complex catchments or watersheds. So in this case, there should be a conversion of the excess rainfall as well. Now, the excess rainfall will be converted to hydrology as well. Now, hydrological cycle, excess rainfall is the amount of rainfall which is converted to runoff. So by what transformation mechanism or process or formulation will will analyze the excess rainfall to runoff. So the transforming excess precipitation into surface runoff. There are techniques which are embedded in this model. The techniques which are embedded in this model under the parameter sections. In transform, there is an option to say transform. So this transform is helping session formulations and techniques which are algorithms which are developed and embedded in this HEC-HMS model in order to deal with transformation of the excess rainfall to runoff. So there are formulations such as unit hydrograph method, such as Clary, Sundry, and SC curve number. You can see here, okay? Clary unit hydrograph, kinematic wave, 2D diffusive wave, modified Claric, and Sundry unit hydrograph, SC unit hydrograph, which we mostly using in hydrological analysis for the investigation of stream flow analysis or runoff estimations in our catchments. And the user specified S graph. So by giving this is user specified, meaning that we should give an input for our model S curve datas, okay, S hydrograph datas, and user specified unit hydrographs. So these are the extensions which are available under this and helping us for transforming the excess rainfall to runoff. The other point, which is very crucial in hydrological modeling analysis, base flow. So there, from the runoff, the excess rainfall, which is transforming into runoff. Addition to that, in our river, there will be an inflow from the groundwater to the river. That's in terms of base flow. So we should take under consideration those scenarios. So this model is to take under consideration this scenario, these scenarios by creating under the parameter sections, base flow sections, okay, base flow. So for base flow analysis, there are various methods which are implanted, like boundary decisions, or by taking under consideration the decision conditions of, then constant Menzies decisions, a linear reservoir, concept, and then linear Wasink for techniques and precision techniques. These are the formulations and techniques which are available in order to deal with base flow analysis. Okay. The other point here is this model also take under consideration the existing, as I said, reservoir. Okay, lakes, reservoirs, pumps, controls, which are available in our catchments. We can also consider them, and diversion structures. The other point, while we are dealing with the stream flow analysis in our rivers, which is available in our catchment or in our watershed, the principle of routing as well now, routing method is a method which is helping us for the analysis of the stream flow characteristic now ridges or river or channels, open channels. So we have full information about that as well now. You can refer the hydrology, engineering hydrology book is okay. How this applicable. So having this information, lag time, lag and K coefficient. So for example, there are a number of methods which are implanted in this HEC-HMS model in order to deal with the routing of the simulation of simulating of the flow in each rivers or ridges. So under parameter section again, toolbar in this HEC-HMS, there is a routing toolbar exists, and under this there are a number of methods which are implanted or embedded under the routing section, okay, like kinematic, lag time, lag and constant K coefficients, and Muskingum Paul plus Muskingum method, which we are mostly using for the analysis of runoff or the stream flow scenario channels, open channels, Muskingum sink, and normal depths, and throttled Saga. These are the number of methods which are available in routing, because these are two key points, especially if we're dealing with this excess or rainfall of analysis. All right. The other point is we should manage the meteorological data in our catchments. So, like, there is a model which is embedded in this HEC-HMS, which is component. Under component section, you can create the model, which is called that is helping us for the management of this meteorological meteorology model manager. There is a meteorology model manager. So under this model manager, there are a number of components. Like here, you can see there is like components which are available, like short wave radiations, like radiations, long wave radiations, precipitation, temperature, dew point. This is for ice and evapotranspirations, and it's now these are the hydroclimate parameters which are embedded in these sections. Okay, all right. So there are methods, especially for example, if we are dealing with the historical precipitation, hydrograph analysis. Okay, so hydrograph method are embedded. So this, and so you can find under this meteorological model. Once you create the meteorological model for your catchment, we can see here like precipitation. Under precipitation, there is a specified hydrograph, frequency, storm, gauge weight. So how we will use the precipitation, the gauges distribution, the rainfall distribution of area. So these are mostly available. For example, this hydrograph method is mostly applicable, and because it take under consideration the data that we give, analyze the outside the program. Okay, so we can the data that we arranged outside the program, and then we can give for the model, and then it will help us for the analysis of the historic precipitation scenario. We'll see the detail while we're doing training. Simulation, just in terms of simulations, how this model is simulated. So we can control our simulation. There is an option that is saying control simulation option, and then there is by combining it with the base model and the meteorologic model, and this control specifications. Like, for example, we can control the start time and then end time. So this is the control specifications are available in the model. Okay, so by combining these three options, at end we can run our simulation. Okay, so we'll see them detailing. All right, parameter estimations. For example, if we are optimizing our parameter, there is an optimization material section in the model. So this is very helpful by optimizing the parameters. Optimizing the parameters in our watershed, in our ridges, those parameters that we are going to optimize in order to come up with an calibrated or optimal output, simulated value like discharge. So in optimization principle, as we know, there is a maximization and minimization. There are two principal areas for dealing with optimization algorithms. For example, linear programming. Optimization, if you are using linear programming, the objective function, so we have an objective function, coincident, and decision variables. So we are going to objective function, like for example, f of x, let's say f of s comma y, and equals to just x plus y. So in this case, this is my objective function, okay? Objective function. So under objective function, I'm going to optimize x and y, which we call them the decision variables, based on the constraints the limit result that I have. I'll give a detailed information about how optimization is working, especially by using linear programming in other tutorial. Okay, in other tutorial I'll give information about that. So here, maximizing the objective function through decreasing the good fit. So that this the model performance in this case, when you are minimizing the objective function, it will decrease the model good fit by taking under consideration the simulated output of the model with the observed discharge, okay, that we are giving for the model. In maximization principle here, it will increase the model good fitness of goodness of fit. If we are using the notion of maximization this model, okay. So what it will do? It will increase the model goodness or fit for simulated and observed discharge, and then it will optimize x and y variables or the parameters definitely in our catchment. So here in optimization, what you're observing here, there are a number of parameters. You have to create a number of parameters. So these parameters are related to the watershed, subbasins, okay, sub-watershed, or sub-basin, sub-basin and river, ridges, and then outlet, okay, outlet or in our catchments. So we'll see that detail. So this is how we will optimize or calibrate our model. And when I'm coming to the installation section, there is a website which was developed by the USAC, that we call it United States of America, USA, sorry, USA, the United States Army Corps of Engineer. This by using this link, okay, just sorry, and by using this, I can copy this link. Okay, this link. You can say HEC-HMS even if by just calling HEC-HMS, okay, HEC-HMS. Then write the name and then on your browser, then enter. So this platform will come, engineering, sorry, hydraulic engineering center. Then click on it. Automatically HEC-HMS will come for you. Then download session. And the download session, there is a current version 4.12. So now in my case, just I'm going to use the old version because I will show for you how the because in previous session I said by using HMS we will try to identify or investigate the runoff hydrograph or hydrograph discharge runoff hydrograph, which was developed by using the um, uh, here related for use. Let me show by using this Clark model. Okay, Clark model by how to estimate time of concentration and the storage coefficients using HEC-HMS. Okay, all right. So then download the newest version. So it will give immediately the application. Okay? No RGB document. There is an RGB versions like version. For example, I'm using version 11, so you have to download. For example, if you are using the window or portable versions, so based on the version which you are going to use, it is given here. So for us, just download the Windows session. This one is for Windows, and so we are going to install in our machine. Just download this one, Windows session. Okay, you can read here. So then download, simply install. Then installation, just once you download the model, so the model will come in this extension, okay? This software is, sorry, This is a software. Then just simply click on it. The installation process will come. Okay. Then say install. Since as I have already installed here, I'm not going to install again, but just for a show purpose. So you have to proceed with it. Okay. Then go. What is saying after removal this program? As I already installed this one, no need of installation again. Okay. But if you didn't have this program before, so it will go. So remove. Yes. Yeah. So I have already installed this model. Let us start. So I have already installed this model. Uh, Now I'm going to give a training. Uh, so this is the again of HEC-HMS 4.11. Open, click on it. Let it come, click on it. So this screen will come for you. Then click on File, then create a new. You can give file name. For me, I'll give well, okay. This is my river watershed name. Okay. Then uh, desktop biological hydrology and HEC-HMS legal. Okay. Method. You can change also the units. USA unit system metric USA custom. Oh, you can make it metric. Okay, no problem. Now the next step is we already seen last time those at component sections while I was giving the theory session. At component section there is buzzing model manager, Terry and database manager, control specification manager. I will talk about that control specification manager, which is helping for the for controlling of the simulation, and meteorological model manager, time series data manager. So these things should be created. Okay. So now, first you have to start from the model manager. Okay. Just click on the model manager. Then the Sabazin, okay. Now ask him what type of buzzing. Let's say Gilgil Giwe. So buzzing one, just simply you can say buzzing one. GG Gil Gil Giwe, okay. Don't give my name, okay. You can give B buzzing. Right. Okay. Now we created GG Gilgil Giwe buzzing. The next step, you have to do reference. Your reference. So there is a JS toolbar. Please just click on JS toolbar. Georeferencing, you have to use coordinate system. Then I'm going to predefine just if you have already model, you can call it from your like if you have a DM which is georeferenced, you can call it from that DM or shapefile. Since I already created, I have a DM in my training. I can call from browse, then desktop. Okay, hierarchical unit. So this is my file. Yeah, GG. No, just stereo. Under stereo. Uh, you can call from here. Okay. All right. All right. So this way you can code. But here you can use predefine. Predefine for simple. For example, I'm located in Ethiopia, so use this common universal transfer Mercator UTM. Under UTM, Ethiopia zone 37, zone UTM zone 37. Okay, Ethiopia is located in zone 37. Where hemisphere is northern Ethiopia, northern hemisphere, and datum WGS. Okay, 84. Then process. Then say sets. All right. Now my buzzing mode is georeferenced. All right. The second step is go to component, calling the Terian data. So the Terian data, just component, go to component, then click on Terian database, then new. So the Terian name will be GG. I'm going to say GG Terian. Okay. Terian. All right. Then you have to call the Terian, your map, data elevation model of your state area. So from Gilgal Given, so this I have already did an elevation model that I developed. So GG data elevation model, then SRA, Gilgal Given, okay, this DM. So here you have to save your DM in TIFF file format. For example, here in my case, I have a DM which is Gilgal Given DM, but it's not saving TIFF file format. So you have to first do conversion JS. All right. So let me open my JS. Okay. Open your JS. Go to your DM. This is my DM. You have to go to your DM. Enrolled per unit. Okay. Digital elevation model. Stir and GB. Or Gilgal digital elevation model. Bring it. Then click on the name under table of the contents. Then data extracts. So just format type, just say GG dev TF, okay? TF. Then select the place where you are going to save. Go to desktop, then Gilgal, okay? I will save this outside, okay? Gil, DM. All right. Sorry, just I wanted to save here in GG. Is you have to select the file. Sorry. Here, just select location. Select the location. So my location should be in uh, desktop. All right, click on desktop file in your folder, and then click on then the file name is saying Gilgal 11. Okay, I'll add here 24. I'll say 24. Okay, for reminder. If you can, no problem. Then save. All right. Now this Gilgal DM24 is come. All right. Remove. Then go to your HEC-HMS. Now you can call Terian. Desktop, GG. So there is Gilgal 24, yeah. This one, okay. This is my digital vision model. Then select, then finish. Now I call the model. Then now this is GG Therian. I already connected it here. So just click here on Basel model. Once you click on Basel model here, it will come. Observe here, okay? So it will come here, Basel model and Basel model Therian data. It shown what? Name. So you have to connect the Therian data, okay? GG Therian, okay? So wait for a moment. So the Basel will come, okay? Yeah. So the Basel is coming. This is my GG Basel. Yeah, it's a little bit busy, my machine. Okay. Okay. All right. So this will be our map. This will be my map. So my next step is our next step will be once you create your Basel model or GLDB Basel. Now the next step is processing the scenes. Okay, just click on yes. It is processing the scene. Click on yes, then process. There, yeah, processing. Okay. Then next step. Now we are going to delineate the watershed for our sub watersheds for my basin. Process drainage. Once you process the sink, you have to process the drainage. So this is a drainage. Mhm. This will be the drainage. For this, we can see how the drainage look like. So we have to create the sub basin. The drainage, okay, you can see drainage lines. The second step, the third step will be first you have to process sink, then drainage, then identify the stream. So we should create a stream based on the sub basins. Okay. So click now. By default, it's using 49 or 50 kilometer square area to create the watershed. Sorry, to create the stream. Okay. By taking under consideration this sub-basin, okay, for each streams. So let us here. Yeah, we can see. All right. So what you have to do in order to see, just click here. click on the button mode screen, right click, then map layers. Then you can unmark, okay, and check these boxes of flow direction, flow accumulation, sinkers, and flow sink is terrain. We can leave the terrain, right? Then terrain and identify streams who can see. Yeah. So you can see the identify streams. Okay, this is the main channel of Legal Giver River, and it is training to so these are in order to reduce. Again, you can put chess identify stream. You can increase. Okay, like I wanted to make it like okay 100 kilometers square. Okay, in 100 kilometers square. Almost it's good for observing variant. This is the stream. Yeah, this is the stream. The main river is available here, and there is 1, 2, 3 tributaries. You can see tributaries. Again, you can adjust till you want. You are not you are satisfying. Okay, identifying stream. Okay, like 150 kilometers square. Okay, identify stream for 500. Okay, kilometer. Yeah, almost we are getting 500. Almost we are not getting the. Well, this is almost a main river. All right, for Gibe, Gilgal Gibe river. Almost I omit the tributaries. Okay, so the next step will be this. I'm satisfied because I got the stream of Gibe, Gilgal Gibe. Now the next step will be once you identify the stream satisfies with it, what you have to do. Um, creation of the breaking point in order to create the subbasins or the creation of subbasin, you have to give the outlet. Okay, so for giving an outlet, there is an option here which saying breakpoint creation tool. Just click on this one, then the plus sign will come for you. Somewhere straight you can click. Okay, right, somewhere straight. Yeah, I can click here somewhere. Yeah, zoom in and then click center somewhere. So this video gets out. Let's okay. Now, once you create these breakpoints, break creation by using break creation tool, the outlet, the go to JS, and then the watershed delineation will be active. Okay, that we call delineation element, which will help us for the delineation of the watershed. Click, then it will ask you subbasin that are going to create it like prefix name. You can give prefix name, give a subbasin like rich prefix name. So I don't just, I wanted to use default and then insert junctions. Yeah, for if there is tributaries, just insert junctions, convert breakpoints. You can say convert breakpoints. I have one breakpoint, no problem. Just no conversion. I already give the name, so they say terminates. All right. Now I get the watershed definition for PVB. All right. Outlets. Sink. Okay. That's nice. That's nice. This is my watershed or basin, PVB basin with how many sub basins? 4 sub basins. All right. So this is how to develop the watershed by using the HEC-RAS. Okay. Then you can extract. If you want to extract this sub-basin, this watershed, go to JS, then extract. Okay, extract layer. Okay, so you can export the layer shapefile. This is shapefile, right? So go to JS. There is an option saying that export layers. So I'm going to export the sub-basin layers. Sub-basin layers. So these sub-basin layers, give the name. I'm going to give just select the place where you are going to extract. So I want to extract here in like Gilgal Gibe, okay? Gil, or you can create shapefile, okay? You can create the folder, okay? Like create a new folder which saying Gil Gibe shape. All right. Then open. Then you can give G Gil Gibe. Okay. File name. Save. Then finish. You can see this one in your JS, OpenJS. Then you can in JS go to this your folder that you create shapefile. Okay, this shapefile you can see here. Yeah. This is going to be shapefile. So this is also one very nice mechanism how to create a shapefile for any subagents based on the uh, that's area detailed elevation model. So, for example, for a country, you can create sub-basins. Or so for a country, you can create by having detailed elevation of any country or any continents or of the world. We can create the good shapefile for basins existing. Thank you. This is good information. So this HEC-HMS have multi-use. So now I have this. So my next project will be um, uh, go to components. I wanted to create the methodological model manager. So click here, then methodologic model manager, say G methodology, GG climate data. Now I create it. Second, again go to components. Since we'll have a time series data for discharge, and now I'm going to show for you. I will have a rainfall data and then discharge data. So time series data manager is needed. Okay, click on time series data manager. Then once now already you have methodological model. So click on time series data manager. So it will ask you like which data time series you want to create, like precipitation I want to create, precipitation gauges. So in this watershed or sub basin, maybe you have several number of stations. So based on that, okay, you can give a time series data of precipitation for each stations by creating these precipitation gauges. Precipitation gauge, then new. So simple, I want to use one gauge for this, for the training. If you have a number of gauges, you can give a number of gauges here, okay? Gauge 1 by giving, again, new gauge 2 like this, okay? So if you have a 10 gauge, then by changing the names, so this way. Now I have one gauge, so I will stop here. For the training, just I will use simple one gauge for this watershed. And then the other point here is, again, a component. In time series, I need discharge at outlet section, discharge gauge for this for model calibration and validation purpose. The new, so gauge 1, okay, just gauge 1. It will come under time series discharge gauge. So here, let's do this, we can take a look down. So we have a methodological model. Okay, we have time series data, and again, for simulation, as we said, we have to create this control specification manager. Just create one control specification manager. All right. Now this is enough for this training. This model, as I said, it will be it is applicable for the multi-purpose, but this scenario plan, how this is an initial input for the model development. So very crucial. You can multiple by from this training, you can use this model for whatever purpose you will to do. So we should give a time series data for our model. Just for example, you can click here on meteorologic data. In meteorologic, I need in meteorologic, I wanted to I'm going to use precipitation. So in precipitation, there are a number of methods specified hydrograph, like standard projection streams, specified hydrograph, inverse distance overlaid, interpolation, precipitation. So I will use the specified hydrograph, okay? So I'll give time series data, and then it will, based on time series data that I give for the station, maybe daily or monthly. So that time series that I give, so the model will do analysis for the rainfall, for the catchment, based on by using the specified hydrograph. Okay. All right. By default, it's there. I have no temperature in this case. If you have temperature, you have to create a temperature again. You have to do it for wind speed, precipitation, down point, and evapotranspirations. Let's come to basin. So I'm coming to the basins. So methodological model. Then there is basins options. So under basins options, you have to include this. Click give you a basin. Okay. Yes. I'm applying for horizontal give a basin. This is my meteorological data data. Okay. For whom? For click give a basin. Okay. Then option. Under option, total overage. Just leave it this, but you can leave it, no problem. It will use default by itself. Okay. So GG climate, then specified hydrograph. Now we are specifying a hydrograph. So click on specified hydrograph in methodology session here. So I'm going to use this hydrograph for all this station for all subbasins. For example, if we have stations in each subbasins, since you create here a number of precipitation stations gauges. Then, for example, if gauge 1 is for subbasin 1, so gauge 2 will be there for subbasin 2. If you have 5 gauge for each subbasins, you will specify here. Okay, now the number of gauges will come here. So now I'm going to use only one gauge for those 5 subbasins. So just you have to select gauge 1, gauge 1, gauge 1, gauge 1. Okay, then say save. Okay. So now I set my methodology. The second control, it will become later. time series data. Let us come to time series data. In time series data, precipitation, okay? In precipitation time interval, I'm going to give precipitation daily, okay? Daily. So from 1 minute time intervals precipitation, it's available here. So I'm going to give the one daily precipitation. For example, if you have longitudinal latitude for your station, you can give here. Okay. Okay, right. And then so you have to say daily. So incremental millimeter. So by using the millimeter, incremental millimeter, then click here, plus sign. Now this is a data sets. Okay. Time from here you are going to start your data. So I have, for example, let us go to you have to I have already data, time series data, rainfall data. Okay, for this model. Desktop, go to desktop. Desktop, time series, okay. But I have time series, precipitation data. All right. Right. Okay. Mm. 996, okay. And so let me create time series data here. Okay, I have already data here, okay. HEC-HMS from there. Time, you have to create time series data. Rainfall, okay. Station range. Rainfall. All right. Yes, I want to call one station that I already you have to create a time series data, maybe daily or uh, let me call. I'm going to call one time series data. Open data and file data source from the desk. Okay, I have already various data. So let me show you. Okay, so here training products. Yeah, then I want to use one of the station this model. Or okay, like yeah, all right. Next change. Still, still, let's find daily RF in millimeter. Daily, okay? Per day. Okay. So format is one. Uh, yes. All right. Format is one. Times. And actually, this data is from 0, 1, 0, 1, 1986, okay? So I am going to bring this one here. Still. So from 19, the data is starting from 19. All right. Can do for all. From here, let's come to, for example, this, the table will come like this, okay, from 01 June like this, okay. I can set my data to be more clear, like this, 4 months. 4 months with format, and date will be in like this, okay. I bet I can set like, yeah, yeah, yeah. 19 to 2000. All right, just click here. Then I can format. All right. Huh? Yeah, format, no formats. Okay, format like this, okay. Yeah, this one. All right, so this one's good. Yes, now I have this time series data, which is starting from the January 1 and 1981 and ending in 2018, okay. All right, so just come here. It's daily data starting from 0 January. All right, starting January 01, January 01, and ending in, you can copy if you want, no problem, December 31. Like, so record is from 9. So we can see the time series data. All right, actually, it should be like this. So Jan 01, okay. January, then what? Sorry, Jan 19. This is 19. Make this one 1986, 18, and December 31. 31. This December, okay. That's 9 and 9. Almost 3, 9 hours. We're not two missing values. Yeah. So now I have this time series. So you can copy your data. You can copy your data. You can copy your data. Okay, copy your data, and then just click on the first one. Okay, all right. Here this. Yeah. Maybe it's one day. Yeah. So here, what you have to use, units should be in cumulative millimeters because we are giving a cumulative daily rainfall data. Okay. Take care of that. Paste. Now my data all come. Then save. Okay. Now all data, I save my meteorological data. All right. The next step will be once you finish your rainfall data, so you can see the graph. You can see an automatic graph, which is yeah, you can see the automatic graph how the rainfall distribution look like. The next step is just gauge for the stream flow gauge. The stream flow gauge data. So I'm going to use the stream flow gauge data daily. Again, I'm going to use daily data, which is meter cube per second, which is manually entered. So you can also give the ID and then even if that to link to for your station. All right, competition. All right, so daily. So let us set our uh, uh, time series data here. Yes. So let us. I have also stream flow data. GG stream flow data. Okay, there is one stream flow that I have here. I'll copy this one to my study area. Okay, stream flow data, time series data. Okay, here my stream flow data. Yeah, it starts from GG stream flow data, which starts from 19. Okay, formats. Again, I'm going to use this one. All right, January 1995 to 2015. All right. So the stream flow data is starting from January 1995 to December 31. All right. December 31, December, let's see in Amharic with list. Let's list 2005, December. So just the sum 9 and then 9. So this will be your time series data. So bring the data. Then bring the rainfall data. All right. Sorry, you just copy your time series data. Yeah. So this is it. Then paste. Yeah. Click. Then paste. So this is times the data. It's a graph. Now save. Now we set the rainfall data that we have. So just simply, I'm going to develop a runoff that will be generated uh, from the precipitation, just from the precipitation that I give us an input to be distributed by in over the area, and the runoff that will be directly generated from it. So the other things that should be set will be the parameter. So once you set this all issue, the next step will be involved for cage one to missing data. Okay. So what you have to do here, we finish it everything. Check, you can cross check. Missing data will be completed. Missing, if there's missing data, just in methodology, if there's missing data, just do set to a default. Okay, that is will be automatically analyzed. All right. The next step will be under parameter section. Now, I wanted to show for you how to determine the time of concentration, and I will going to use time of concentration for the in case if we are going to use transforming the excess rainfall to runoff by using the Clark unit hydrograph method. Okay. I would use a Clark unit hydrograph method. So in order to use Clark unit hydrograph method, this HEC-HMS, as I said, version 4.11 can help you to determine time of concentration and the storage coefficients in order to determine the runoff that will be generated. All right. So in order to do this, first, what you have to do, just characterization. There is a characterization under parameter. There is characterization. So characteristics. Then click on characteristic. Then sub-basin. Go to sub-basin. So for the sub-basin, all those sub-basin characteristics will be calculated for Gilgit basin. Okay. Like here, for example, sub-basin one, the longest flow path length is this length, and then this in slope, centroid flow path length is controlled, centroidal flow path slope. Okay. So I'll take you back in order to calculate for calculation of the computation of the storage coefficients. For computation of the storage coefficients or the using Clark model and the time of concentration in HEC-HMS, there is the calculation which are developed, as I said earlier. So here there is some analysis which done for the dam safety and Pennsylvania, okay, and this at end this is recommended. The time of concentration analysis should be recommended, for example, if we are using HEC-HMS. So this is a general formula that will help us for the calculation time concentration in our catchment. And this is a general formula that will help us for the estimation of the storage quotient for the caloric unit hydrograph parameters. Okay. So in this case, so you have to extract the time of concentration, which should be extracted for the long flow path, should be none. This should be none. And then centroidal flow path, and then average slope of the flow path should be extracted first. So how will do it? Just follow me, okay? Then at the end we'll give this equation code, and then we'll determine the time of concentration at the R value, okay? All right. So let me show you how we do it. So the first step is just go to the parameter and then characteristics, then subbasin. One in subbasin, just extract those two parameters. Okay, I will tell it for let me sorry. Okay, end up at this slide view. So okay, just I will take this one here. All right. Mm. All right. So this is so we have to extract the longest flow path first. So this longest flow path for all my sheet. So just select all, then there is exports. Okay, exports. Where we are going to export, then you can give this longest flow path name. Okay, this name. Sorry, the first one, time of constant. Yeah, longest flow path. Longest flow path. Copy, or you can write there. Then go to your give. Okay, this is Google Give, right? Automatically it will take you there. So give, you can longest flow path. Okay, longest flow path. Longest flow path length. Flow path, longest flow path length. Okay, length. Longest flow path length. Just give. Okay. Exports. Again, the second step will be centroid. What centroid flow path? Centroid flow path length. Okay, this one. Okay. Then again, exports. Before exporting, just open, say, paste, centroidal flow path length. Okay, length. Problem. Centroidal flow path length. All right. All right. Then they open exports, and where the other is LLC and slope average of the flow path. Now, this one, which is written as yeah, which is written as slope. Okay. All right. Come here. Average, or that's average flow path length is slope. This one. Okay. Then select. Go to average flow path slope. Yeah. Open exports. All right. Now we finish it exporting of those to our model of for folder. So the next step will be just so the next step will be competition of put parameter then transform. Now I wanted to set these for all for this river basin, right? For Gilgit. So go to parameter transform. And we're going to use and while I'm transforming the excess runoff or precipitation to runoff, I'm going to use a Clark intergraph. Okay, so just click on other, then select Clark intergraph. This will be applicable for all subbasins. All right. So here, in just once you did this transformation, just click on Clark intergraph. So in Clark intergraph, it will ask you time of concentration and the storage coefficient. As we said, this is a parameter which is an input for the Clark model in order to estimate the Clark unit hydrograph. Okay, unit hydrograph analysis. So there is calculator. Okay, at the end you can see calculator. So just click on calculator, then bring the formula. This is a formula. Just bring this formula. Already set. Copy the formula and then just come here. Paste here. Okay. Control plus. So this is my calculation. So time of concentration, it will calculate time of concentration for you. All right. The reason why it's not working, because here MI, okay, the unit that we use it here is use it here is not MI. So you have to manage that unit. Just go to tool, program setting. The unit that we use it here is default. In default, we are using metric, so make it USA. Number of cores, hydraulic, okay. Canopy, okay, then okay. Now, now go to subbasin characteristics and then recompute. Still now it is in okay. So you can go to edit, sorry. Program setting. Publishing, okay. Yeah. So now I think we can, yes. All right. Yes, let us export again. All right. Those are for these longest floppers. Longest floppers. Yeah, you can also actually go to here in order to time of concentration, like time of concentration using HEC-HMS. Okay, so directly it will take you to user maybe while I'm copying it, if there is some problem, it will go down here. You can go down, and then there is this formulations. Okay, then you can copy from here. This is a code. If not working, okay, I will extract again. Let me try once again, and then okay. So let's yeah, just parameter characteristic. Okay, sorry, transform cleric. Then you can take a copy cleric. Best. Okay, then compute. Also computes. Syntax: no variable alternative at inputs. Flow pass. Okay. So yes, you can copy this one. All right. Copy. Yeah. Just you can. Yeah. So let's try once again. Characteristic. And because you see the unit is making this problem. If so, then exports. Okay, the first one, limit purpose. Just take this one. Limit purpose. Okay. Let me use this one. Yeah? And then limit purpose. Purpose. Yeah. Then second step, centroid. Copy. Centroid. Flow length. Centroidal flow length. Centroidal flow length. Extract. All right. Control plus V. Centroidal flow length is open. Extract. And the third one will be this one, right? Yeah. Is discussed. Okay. Yes, okay. And then the third one will be flow as slope. Flow as slope. Okay. I compute. I compute. Apply. All right. Okay. There is some mistake you can see here. What thing could not permit writes. So again, go. So Brazil. Then is this one. Extract. That's yeah. So I think it's there's some other functions are there. That's why I said like this. Completely. And then it's alright. Clear. I got you. Now transform Claric. So this is actually helping us how automatically you can calculate. Okay. Hmm. So this issue is occurred due to the unit problem. So we should initially, actually, while I was developing this training, what I did, I just I use a units. It should be US, okay? Yeah, unit should be US. So let me again the buzzing characteristics. Yeah. So initially, while I'm developing uh, the watershed, okay, I use it. Yeah, I use it. Yes, yeah, that's why this problem is happening actually. So I think. Mhm. Yes, apply. Yeah, and then characterize which characterize. Yes, now it will function. Yeah, now we change it, right? So, Bazen, you should set up your Bazen. It should be in USA. Okay, so if you make it here, so you just click on your Bazen, and then under Bazen there is a unit saying USA, USA customary. So, because this formula, as you observe it from here, this clear formula is in mile, okay, mile. So now I think the model will properly function. It will work properly. Now, what we have to do, just we should go to parameter, subbudget, just extract now, okay? Just copy, extract, go to flow, the longest flow path, uh, longest flow path, all right? Longest flow path, open, extract, then replace. Then the second centroidal flow length, extract, go to centroidal flow path length, centroidal flow path length, yeah, replace, extract, centroidal flow path length, open, replace, and then at end this slope, okay, export, uh, this one. All right. So now the unit is managed. So let us see now computation. Okay, go to those. Sorry, transform, calculates. Yep, perfect. Now it's done. So the unit have, as I earlier said, unit have a high impact, especially while you are using, if you are using your take of the unit. Okay. So I already showed you how you convert the units uh, to the mile scale rather than kilometer scale or meter scale. So just you have to manage your buzzing model, okay? Under buzzing model, as I already showed for you, just unit system should be USA, not metric. Okay, just make this USA and then go to raster and then just simply, sorry, go to a parameter and then characteristics, then compute first sub-basin, just recompute the area and calculate. Okay, recompute the area. Okay, parameter sub-basin area, recompute the area, and then okay. All right. So this is a way that's the second formulation. Now we just copy this formula. Okay, copy this formula. Then come to calculator. All right. Let me remove this one, okay, because it will make confusion of yours. Then it's so okay. So just with parameter transform cleric. So under cleric at the bottom section there is calculator. Okay, just click on calculator. So here field, the outer field is time of concentration and storage. So first you have to determine time of concentration and then multiply the time of concentration with factor 3 or 7, right? The factor which is given for us. All right. There is a factor, right? So yeah, this factor, time of concentration, and the storage coefficients. Yeah. Okay. So here the factor. Okay, I have already factor is 3/7. Okay. Now paste here. Your model, then let's say calculate. Now it's automatically give you here the value. Second, just change the storage coefficient again, multiply this by this 3/7, sorry, 13/7. You can multiply just close bracket 13/7 multiplied by. All right. So the model will calculate. So this is for the storage coefficients. Now at the end, what you have to say in order to apply it for all your this to come to each sub-basin parameter, just there is an apply section here. Okay, so one you are saying apply. So these values numbers will be changed to the black. Okay. This means now we applied it in your model, right? You can check in here, like the Clark intergraph. Okay, so under Clark intergraph, automatically it comes for all subbasins. Click on subbasin, just SC the parameter which is Clark intergraph, which will help us for the conversion of the accelerated file to runoff. For each basin, the time of concentration, the storage coefficient is set. All right. So the next step, just the next step will be now we set for each basin the runoff process and the access runoff to runoff conversion mechanism by using Clark intergraph. The second, so I have no base flow data, so I will not use a base flow data. Losses, we can associate the curve number method. Just I'm going to select the curve number method. Okay, in order to loss, we can set curve number method based on the Lansdowne curve characteristics of the catchment. We can set up the curve number method. Okay, and based on the rainfall data, Lansdowne curve characteristics of the catchment or the watershed or sub-basin. So having this concept, you can set for each sub-basin the curve number. So I'm going to select this one for all, okay? So initial, while you are setting the curve number, it will ask you the initial abstraction in the curve number for each river basins or for each sub-basins. So Okay, initial abstraction, just you can leave it as leave it, but you can set the curve number. Okay, this is our critical point here. So curve number 80, let's say I'm going to set, okay, the region, like curve number of based on the catchment curves and land cover and the rainfall distribution runoff characteristics. So curve number, let's say 80. Okay, 80 for the curve subbasin 4, and then 70, like 65, 70. So it, as you know, while you are using the curve number method, so those unsense soil moisture condition 2 are going to use uh, unsense soil moisture condition 2. Okay, so there are various methods. You can see how curve number CSC curve number method is helpful for estimation of this curve number. So in the next section, if I have a time, I will show you how to determine curve number for catchment or subbasins. So let's say we estimated like 70. So I can apply this formula. Now let's say apply. So now curve number is applied for. You can see which are obstructions or not. Surface floor and not using any surface floor. Okay. So we are saying that the runoff will 80% of the rainfall which is occurred will be converted to runoff. We are saying that 80%, right? All right. The other point is simple surface canopy. You can see the simple surface canopy, and it's now that since I have no information on this, just okay, I will use only the curve number just to and declare a method here for in subbasins for the analysis of conversion of excess rainfall to the runoff, right? So I'm going to omit this simple canopy and a simple surface. So here you can go to tool, yeah, set program. Okay, into set program, just defaults in default subbasin canopy characteristics. Okay, if you have canopy really simply canopy, so you can give those, but I have no information now on this hand. So just I'm simply using default none. So subbasin surface, just I'm using the okay, you can dynamic surface. Okay, so you can simply say okay, simple surface. All right, so and simple surface, so go to parameter canopy, I'm going to use a simple surface, or in parameter you go to canopy and then change none. Okay, you can use none. All right, parameter canopy change method then none. So we will not use a canopy under consideration. Okay, just go to parameter canopy, change just canopy none for all. Okay, click first on the basin. First you have to click on basin. If you click on subbasin, it will change already for one subbasin. So just click for basin hole, like for now my case, Gilgil. Okay, so easily you will then go to parameter, then canopy, say the defaults. Parameter canopy surface. Okay, loss, we already set the curve C curve number for all. Transform, we done. Base, we have no. Centimeter, we have no. But we have to set routing in our channel or river. So I'm going to use the masking gum, or you can use lactine. Since now we have So you can use like Buckingham normal depths, like dynamic kinematics. So if you know the lag, okay. So now I'm going to use a Buckingham, which is known method and say on very limited, which are mostly used for analysis of the flow characters in channels, open channels. All right, now I said miscongram for all hat reaches. You see now channel loss I'm not considering, but miscongram I'm going to consider. For reach, do the same. We have two reaches. So in order to set it for all, what you have to do with code parameter, click on assume code parameter. So routing just miscongram. It will initial type, flow type inflow, okay? Yeah, inflow which are coming from Missingham Kahauli and this. So there are standard values for these Missingham values you have to set. For example, for Miskingham X, just mostly it is recommended from, I think, from 0.1 to 0.5. So let us use this one 0.1 for 2 and 0.2 forward, and then this mostly just I think from up to 1, okay, from 0. From 0 to 1, I think it's recommended. So it has 0.5 and 0.5 forward, okay. There's something different, but you have to use the exact value. Then you have to say apply for. So it will apply this for all um, ridges. So the other points here, just code parameter, ridge we done, base we done, loss we done. What else? So okay, now we set this for all. The other point now Miskingham sets, all right, sink or the outlets. We should go to an outlet sink. Outlet description, okay, options. Observed in outlets, we have an observed flow, yes, gauge one, okay. We should give a gauge one. All right, now we set everything. Yes, cross check, okay, one cross check. Surface flows. Ah, okay, so here is some issue. Surface loss in loss. Yeah, surface loss. Go to all for this. Surface loss should be, I have no information on surface loss, so for surface loss we already done, we transform we already done, okay, and observe it flow, no, subbasin you have none. And again, for subbasin 2, you can see, yeah, by default, it will give you subbasin 3, subbasin 5, subbasin 1. Yeah, all right. Sync option, we already run. All right, now, what's remaining? Control, okay? I'm going to control my simulation. Just, we have to control the simulation. Computes. So go to control, you can set up your simulation time interval, okay? Like it is a simulation, the In control, you can give the time period that we already used earlier. Yeah. Let's say simulation. Let it do a simulation for me from January and to 2000. So you can control here. This control is, as I said earlier, for use. 01 December, January, okay, January, okay. Uh, I am going to do a simulation to be done for collaboration validation. So for the 1995, okay, 1995, 09, right, there, 0. In date of simulation, 0, you can give no problem. 31 December 2005, okay. End date, end time, like 09, 00 minutes. So simulation interval, okay, we are setting it controlled time 15-minute intervals. Let us do hourly or to give it that hourly. So like 15-minute interval, it can do a simulation for me. Compute. So the last session is setting the simulation manager. Okay, so compute, go to the toolbar compute, then simulation manager, then new simulation, then go finish. All right. Now I have a control one I have. So simulation control specification is here. You have to ratio method, precipitation, so no ratio method, and save. Now I'm not going to save the data. Just I'm going to do simply simulations. Okay. Basel model, this one, methodological GG. So as I said earlier, simulation will combine the Basel model, methodological model and control specification. Okay. And then at the end, it will give you a simulation outputs, right? So let us then, once you set up the simulation, just use a computes. So the model will compute for you and give some warnings. Yeah. So simulation is ongoing now. So this is all about HEC-HMS, how it is initial setup. So for this training, I'm just setting, for example, in methodological data, I'm giving only like few datas. In stream flow data, I'm giving few datas. For example, if you have a reservoir, you have to give a data like the gauge data in terms of flow stage data, river stage data. So multi data you can give for the model. So once you set up properly for your model, it will give you the exact runoff that is, or the stream flow that will be occurred from your catchments for each subbase for total watershed. Is all about HEC-HMS model training. Thank you. Let us see. Almost approaching 99%. Okay, 95. So I'm going now. Now almost were done. So our simulation is done. So we can see the result. Okay, compute then results. So now there's results. Just go to simulation run result section. So here we'll set up this one. I'll show you. In order to get this calibration summer output and global summer output. So global summer output is coming. Okay, global summer output is coming, and it's showing us peak discharge when the peak discharge happened. Like for example, in sub-basin 1, peak discharge happened 19 in 4th June 2024, like that. Okay. Yeah. All right. So we can see at which reach, for example, peak discharge occur in a peak discharge occur, for example, in reach 2 in 2000 again. So July 2004. So for example, in order to get this calibration summer is not coming, right? So what you have to do, just come here, to go to just go to parameters. In parameter computations, just you have to select the computation point parameter. Okay? Here, this one. Click on that and select the elements. So I'm going to sync. I'm going to select sync. Okay. Then back here, go to sync, then parameter setup. Okay. You already parameters. So